So hello, today's topic I am going to discuss with National Quantum Mission, going with better technology, going with more science, more research in India's own unique way. So to start with, we have to discuss with the quantum technologies. What is the term quantum? What do we need to know about quantum computing and classical computing, classical science and quantum science, their difference? We have to discuss a lot about it. So to start it, let's see a quote of Richard Feynman, who is a great Nobel laureate in physics. Nature is not classical, and if you want to make a simulation of nature, you would better make it quantum mechanical. And by golly, it's a wonderful problem because it does not look so easy. So quantum mechanics is not so easy, that Richard Feynman had already said this. So now come to the quantum technology. What do we mean by quantum? Matter behaves in a very unexpected and counterintuitive manner in its smallest scale. Just like in nanoscale, matter behave in very counterintuitive manner in the smallest scale. Subatomic particles such as electrons seemingly exist at multiple locations at the same time and can influence the behavior of a like particle with which they have had a prior interaction over infinitely large distance. Quantum materials are class of a matter or systems that allows us to exploit some of the unique property of quantum physics and accomplish tasks that classical technologies are incapable of. Means in the quantum technology we can discover so many things, we can allow us to exploit those things which in which classical technologies cannot reach even. The concept of quantum material was originally introduced to identify some of the exotic quantum systems, including unconventional superconductors, including heavy fermion systems and multifunctional oxides. It has now morphed into a powerful unifying concept across diverse fields of science and engineering, including solid state physics, cold atoms, those atoms cooled to close to absolute zero temperature, whereby their quantum mechanical properties are unveiled, material science and quantum computing, so as to say. Now, some of the properties like the ability to exist in multiple states at the same time, which we call the phenomena of superposition, can be used to perform real life tasks that conventional classical technologies are unable to achieve. Quantum computers are already a reality, though their capabilities are quite limited at this point. So after 40 years of delivering this quote of Richard Feynman, quantum computer has now become a reality, but its scope is still limited. Now come to the discussion of conventional versus quantum computers. What are the difference between them? Can we do all the things in quantum computers just like the conventional computer? The answer is yes to no. Why yes to no? Because we have to use classical computers. Not so many tasks we cannot do so many tasks in quantum computers just like classical computers. Conventional computers store and process information in bits. Okay, a bit is the smallest unit of data that computers can handle it, or so as to say classical computers can handle. It can take just two values, 0 or 1, but only one of these, 0 or 1, only one of these at a time. A 2-bit system in a conventional computer can have 4 states, either 0, 0, 1, 0, 0, 1 or 1, 1. But again, only one at a time. To go through each of the 4 states, the computer has to take 4 steps, not simultaneously. A more powerful computer can speed up the process, but it would still have to go through the 4 steps again. So this is where quantum computer starts doing things differently. Superposition makes it possible for the quantum bit or qubit that is called to exist both 0 and 1, both state simultaneously. That's the application of qubit, where bits cannot reach. What it means is that quantum computer can go through these 4 states in one step, unlike conventional computer that requires 4 steps to complete these 4 steps. Okay, now you can ask me, what are the application of quantum computers? The applications of quantum computers are in heavy research or discovering precise drugs, or in cyber security, all those high precision weather forecasting, or predicting about climate change. All these predictions can be done more accurately with the invention of quantum computers. But we should not think that quantum computers can totally replace the classical or conventional computer. In our laptops or in our day-to-day life, we still need the classical computer. We still need the classical things in our laptop. Along with that, for more precision, we have to use the quantum computers. So we have to go in a hybrid way to better our research, to better gain our result in those highly technological research, high precision drug monitoring, all in all this area. Okay, so after this, let's come to the topic of what is required from our quantum mission. Research will be required to develop low loss materials for superconducting quantum electronics that preserve quantum information over a long period of time. Novel semiconductor, nanostructure for the high brightness source of entangled photons, and much more. The impact of much of the research cut across multiple verticals of quantum technologies, and this necessitates dedicated and centralized material or device infrastructure. This will allow streamlining the material and device requirement for the core quantum technology verticals of the mission. Building infrastructure for new materials and devices with in-house research and development, synergizing the diverse and geographically distributed material workforce in India to achieve mission deliverables, and ensuring efficient resource utilization as well as minimizing redundancy and duplication. So why are we looking for this quantum mission? You all know that we have a large number of IT workforce. We have a talented researcher base. So with this, we must go with this quantum mission along with other developed countries. We should not sit in idle. We have to exploit these talents just like other developed countries are doing, like Germany, like UK, or so as to say US and China. The quantum materials and devices component of National Quantum Mission will bring innovation in the field under common umbrella, and this is the need of the hour. Now, achieving this task will require leveraging the evolving scientific infrastructure in the country and aligning with some of the key national mandates. Capacity building, which is the key in the past 2 decades under national initiatives such as Nano Mission, has enabled 5-fold increase in research publication in the area between 2011 and 2019. Several institutions are endowed with expertise and facilities, including excellent infrastructure for semiconductors like TIFR or Tata Institute of Fundamental Research. There is a strong community of material modeling and computing expertise supported by National Supercomputing Mission and other local computing facilities. Now, what is the target of the mission? The goal of the mission is to seed, to nurture and scale up scientific and industrial research and development and create a vibrant and innovative ecosystem in quantum technology. and timeline of this mission is 2023 to 2031. Long 8 years. With the launch of this mission, India will be the 7th country to have a dedicated quantum mission after US, Austria, Finland, France, Canada and China. It will target developing intermediate scale quantum computers with 50 to 100 physical qubits in 5 years and 50 to 1000 physical qubits in 8 years. So we have already achieved the 7 qubits quantum computers, in which the TIFR is involved with TCS. We have already achieved that. We have already enabled that technology. The mission will help developing magnetometers with high sensitivity for precision timing, communications and navigation, so as to say. Now come to the advantages of quantum technology. Why do we need quantum technology? To all know that quantum technology has some increased computing power than the classical or conventional computing technology, and it has some improved security corner. So for this it has an edge over the classical conventional computing in the cyberspace or in the cyber security domain. It can do faster communication. It has enhanced AI application. AI is a reality today, and we have to do much more with this AI along with this quantum technology, and better sensing and measurement, for which we can use it for precise drug delivery and higher kind of drug invention, precise forecasting of weather, climate change monitoring. All these things we can do with the better sensing and measurement of quantum technology. Now come to the disadvantages of quantum technology. We have to be sure that it is quite expensive than classical or conventional technology. Don't think that quantum computers are like supercomputers. Supercomputers are just like classical or conventional computer. They come at heavy cost, but quantum computing is more expensive than even supercomputing missions. It has limited application. You cannot say that in your laptop you are going to use this quantum technology for your personal use. Okay, so you have to use the conventional computing there. In case of limited applications like drug delivery, like high research level atmosphere, like some precise weather monitoring, like some data about climate change, like some high security cyberspace, all there you only need this quantum technology. So limited application and sensitivity to environment, and this you have to make sure that quantum computing has a sensitivity to the environment, sensitivity towards the temperature of the ambience. So you have to regulate the temperature where you are maintaining the quantum computing facility. So you have to maintain that low temperature to get better advantages from quantum technology. And obviously limited control. Not everyone can control this, and that's why you need to have a better workforce which have the proper training to deal with the quantum technology. Now come to the funds allocated for quantum. So now I am going to discuss with some data regarding our quantum mission. So the fund allocated by Government of India is rupees 6,000 crore, around 0.75 billion US dollar for the 2023 to 2031 national quantum mission, where China is estimated to be investing $15 billion in this effort, and US is pumping about 3.75 billion US dollar, which is much more than this figure. The UK has put about 4.3 billion US dollar, and countries like Germany, South Korea, France have all committed to spend more than $2 billion. So in India, we are underspending behind this mission. We are already few years behind in research facility in case of this quantum technology than those countries. Again, we are under financing the project than these other countries. Next, come to the paper published on quantum or quantum technology, so as to say. Between 2000 and 2018, Indian researchers have published 1,711 papers on quantum related science according to one publicly available database, whereas Chinese and American researchers have published 12,110 and 13,489 papers respectively. 7 other countries have published more papers than India during this period of 2000 and 2018. Among 10% most cited papers, the US and China lead again, and India ranks only 20th. So here also we are behind those developed countries. Now come to the facts of patents registered. China and US are also garnering a lion's share in the number of patents being registered. Between 2015 and 2020, Chinese and American researchers acquired 23,335 and 8,935 quantum related patents respectively, whereas Indian researchers had only 339 such patents in the same period according to a patent database. India was ranked 9th by the number of patents obtained. So these are the area where India has to face tough competition from the global players. So it is a tough race, but don't think India is not in competition. India is declaring itself to be in competition by just launching this mission last year. Between 110 and 145 senior scientists were currently leading research groups on quantum related technologies in India. These groups supported 75 to 100 postdoc fellows and about 400 PhD students. In addition, about 200 senior scientists were working in the related fields of material science, electronics, computer science and quantum physics, so as to say. Outside European Union, India is the largest number of graduate students country in disciplines aligned to quantum technologies. There were more than 82,000 such students enrolled, which is even more than China and US in case of quantum technology related topics. So these were my discussion regarding quantum technology, national quantum missions, and where do we fall short in the national quantum mission in case of quantum technology or than those developed countries. So to end with, I want to show you a book. It is available in PDF form in the IBM website. It is published by IBM itself to generate awareness about the quantum technology. The book's name, the PDF is available in the name of the Quantum Decade. You can visit in the IBM's website or just Google the Quantum Decade by IBM and go to download their PDF. You can know more about this quantum technology. You can have more awareness about this quantum technology. How do we going ahead with this technology? How is the world moving forward with this quantum leap? So thank you for being with me. Have a good day. Bye.